I'm Ben Rapoport. I'm an electrical engineer and neurosurgeon, and I'm here today to answer your questions from the internet. This is brain-computer interface support. Winnie Cherian asks, how does brain-computer interface technology work? Brain-computer interface technology uses the fact that the brain communicates with itself and with the outside world using electrical signals. And so brain-computer interfaces are implants that use tiny little electrodes that touch the brain and transform the electrical signals from the brain into ways of interacting with computers and external devices. That translation of electrical signals into useful means of communication with the outside world takes place using machine learning algorithms that transform the digitized bit streams from brain electrical data into means of communication with computers, smart devices, and in some cases, robotics. Instigator asks, could anybody explain to me why a human being would even want a brain-computer interface implanted in him/her? I only ask because it's happened. Well, I think it's important to understand that one of the early uses of brain-computer interface technology is especially for people with disorders of the brain and nervous system. And I'm talking about people with spinal cord injury, stroke, and some forms of neurodegenerative disease, such as ALS, conditions that paralyze people and leave people with totally functioning mind unable to interact with the world in the ways that many of us take for granted. The first generation of brain-computer interface technology is really geared towards enabling people with those kinds of conditions to interact with other people, with the outside world, return to work, and have a sense of dignity and independence that many of us take for granted. Govald asks, can you move a cursor in your mind or draw using a cursor? That's how BCIs for blind people work right now. Everything needs to be drawn, aka sequential, instead of all at once. Let me try to unpack this question. How do you move a cursor with your mind, or how do people with brain-computer interfaces learn to move a cursor using their mind? For each person who's had this experience, it's a little bit different. At the beginning, we usually provide an instruction. Think about moving a joystick, or think about moving your hand, or think about moving your arm. At first, it's very laborious, and eventually the brain just connects to the cursor, like you learn to use a tool, a pencil, a baseball bat, or riding a bicycle. So that the brain-computer interface is a tool like any other. And we're still really learning what that experience is like and how the brain accomplishes it, but that is the subjective experience that people who've used this technology explain, that it sort of clicks at some point and it starts to feel like magic. You know, when we interact with the real world, we don't realize it, but there's actually a delay between what our brain thinks and tells the body to do and when the body does it. In a brain-computer interface where the interaction takes place directly between the brain and an electrode, we can bring that latency down to individual milliseconds. That's why people feel like the experience is almost like the interface is predicting their thought. There's another question that's packed in here. Can brain-computer interfaces manifest a fully formed thought? That gets to the question of how we subjectively feel like we're thinking. Very often we imagine something, or we have a feeling or a picture or a concept in our brains, and we don't right now have a way of expressing that fully formed thought other than through drawing a picture or speaking in paragraph form. But we do have this subjective sense that thoughts exist in a fully formed way, and there's this question that I think Govald is asking, which is, will brain-computer interfaces allow us to transmit thoughts in that fully formed way? I have a feeling that the technology will allow us to travel in that direction, probably even faster than we can imagine, even if we can't say exactly how right now. Pesh909X asks, will BCIs ever be able to record our dreams and psychedelic trips to video? And the answer is yes. Brain-computer interfaces already can see activity in the visual cortex, which is the part of the brain that processes visual information. And there has been some work showing that actually some of that information can be decoded to recreate the visual scene. There is some evidence that that kind of visual replay happens during our dreams. And so it may be possible in the future, just as some of these studies have begun to show, that brain-computer interfaces can record, replay, process the information that occurs during imagined visual activity and dreams. Stephen Roto asks, the first human patient with a brain-computer implant used the technology to successfully play Mario Kart? If that isn't the definition of a 90s kid, I don't know what is. It is true that the first Neuralink patient used his implant to play Mario Kart and seems to have had a great time doing it. That wasn't the first human patient with a brain-computer implant, but he did use it to play Mario Kart, and I think that points to the fact that people are going to use brain-computer interfaces to do all the sorts of things that we take for granted and know and love can be done in the digital world. Fashion Savage asks, will BCI lead to security issues of hacking or reprogramming people's brains? This is a really important question. It's one that many people have asked, which is, given the sensitivity of neural information, will BCI technology lead to issues involving hacking or compromising the security of people's private thoughts? Certainly in the first generation of brain-computer interfaces, we're really interacting with the parts of the conscious brain that move the body, move the hands, move the arms, move the face, and the muscles that control speech. And these are not really areas of the brain that we consider private thought activity, and furthermore, patients, when you ask them, would you be concerned about a privacy issue in this context, many of the people who stand to benefit from this technology would trade a little bit of privacy for the ability to interact smoothly with the outside world. But that doesn't minimize the possibility of real security and privacy issues when neural data is being transmitted wirelessly outside of the body. So we and others involved in the industry have taken real care to try to encrypt and secure any neural data streams that leave the body. Real Editor 6 asks, I was wondering if ever a human brain merged with an LLM via a brain-computer interface, what would the AI experience? What would that person experience? Is anyone connected already? The answer is a qualified yes, because people with brain-computer interfaces now certainly have the ability, using the same means that we do, of textually querying an LLM. And so that interaction is definitely happening. I haven't asked the AI what the AI's experience is, but certainly we can do that. I look forward to that question. What would that person experience, I think, is actually very similar in the current form of the technology to what you and I experience when we query the AI. Those interactions right now are textual in nature. The AI's output is not fed back directly into the user's brain just yet. So the BCI users have an experience that's similar to what every other user of an LLM has. But I get the question is asking towards a future state in which there's a more symbiotic meld between artificial intelligence and humans through brain-computer interfaces. And I think this is the direction of travel, and it's hard to predict exactly what it's going to look like. James Rosenbirch asks, what part of the brain is the BCI interfacing with? Many brain-computer interfaces to date spend a lot of time in and around the motor cortex, which is this area of the brain. This is the hand motor area. This is the leg motor area. This is the face motor area involved in speech. Those motor areas are really important for current generation brain-computer interfaces because they perform the computations in the brain that allow us to interact with the world physically. When we think about things like typing or moving our hands or walking or speaking, those are the parts of the brain that serve those functions most directly. But there certainly are future directions of brain-computer interface technology. We can think about connecting to and interfacing with other areas of the brain and other areas of the nervous system. So areas that control sensation, decision-making, memory, even parts of the brainstem and spinal cord that are involved in other types of neurological disease. Our friends at G-Tech Medical Engineering, how many electrodes are needed to run the brain-computer interface? The answer to that is in the hundreds or thousands, and that just gets us off the ground. I think it's hard to say what the upper limit is to functionality. So many of us are familiar in the world of communication that basically the higher the speed of your connection, the more sophisticated the applications you can run, or in the world of images, the more pixels or megapixels you have in your display, the higher fidelity the graphics you can render. And the same is true in brain-computer interfaces. The more detailed and the higher resolution the picture of brain activity you can generate, the more smooth and sophisticated the real-time interaction you can have with the brain. Right now we're seeing that brain-computer interfaces with around 1,000 electrodes get us off the ground to incredibly high levels of functionality that include things like controlling a cursor, performing the sorts of tasks that we take for granted in everyday interactions with computers, but we can see a path towards many thousands of electrodes and even orders of magnitude higher in which smooth, intuitive connections between the brain and the outside world will be even higher performance. OK Hunter 8210 asks, considering recent developments in brain-computer interfaces, I'd love to hear from experts or enthusiasts about potential applications in assisting individuals with severe paralysis or ALS. Have we made sufficient strides toward leveraging BCI technology for rehabilitation purposes? Yes. Severe paralysis and ALS are really the first conditions that have received a tremendous amount of attention for brain-computer interface technology. There's quite a few examples of patients in clinical studies who've had tremendous benefit from their implants, quite apart from being part of the clinical studies. And it's exactly these individuals with severe paralysis from spinal cord injury, certain forms of stroke, and ALS will be among the first to benefit from the technology. A Reddit user in the Singularity thread asks, is there a concrete pathway to non-invasive BCI technology? Mostly no in the way that we think of, but also yes to the implied question of, is there a use for non-invasive neural interfaces. So when I think about brain-computer interfaces, I think about systems that are being used to drive real-time interactions between the brain and the outside world. And that kind of high bandwidth, sophisticated, smooth, high-speed interactions between the brain and the outside world that really happen at the speed of thought, that requires implanted technology. There's no way that we know of around the need to actually be touching the brain in some way to get that kind of high bandwidth, high speed interaction. Non-invasive techniques and technologies have captured scientists and neuroscientists' imagination for a long time, and there definitely is a use for non-invasive technologies. They can detect brain state, they can manipulate brain state, and they can be used to treat certain forms of disease, but not to manipulate at high fidelity and high resolution in real time. At Howard G9263 asks, brain-computer interfaces sound cool, but kind of scary too. Like, what if it malfunctions or something? So many important technologies have these sorts of questions attached to them, whether it's cars or airplanes or gene sequencing or artificial intelligence. There's always this question of it's magical when it works well, and what if it doesn't work well, or what if it malfunctions? It is important, as in the development of all kinds of technology, to have ways of fixing things when they go wrong. You know, Murphy's Law is real. Anything that can go wrong will happen in some way. And so we need to try to anticipate failure modes and plan for how to fix them. We've developed electrodes that interact with the brain in a way that doesn't damage the brain. And so these electrodes can be moved, removed, replaced, and upgraded as necessary in the future. And other components of the system can be modularly changed out over time. For example, the battery or the wireless or certain forms of tunneled connectors that are implanted under the skin. So understanding the way things obsolesce or change or may need to be switched out in the future is important to ensuring that we can safely repair a device and plan for all eventualities. Queen Guinevere asks, imagine what happens when an implant becomes obsolete, is no longer supported, and becomes increasingly vulnerable to hacking the longer it remains installed, and you can't uninstall it without surgery. Like, imagine if you had the equivalent of flash implanted in your brain. This is actually a really deep question, and it gets to the notion that all technologies have a cycle, and you want to be able to plan for upgrades and plan against obsolescence. At Precision, one of the ways that we've thought about this question of obsolescence and the potential need for replacement is to develop an electrode technology that's based on thin films. This is the Precision electrode array. If I turn it on its side in this way, you can see it's incredibly thin. This film coats the brain surface with electrodes rather than penetrating the brain. The idea is that those electrodes could be removed or upgraded over time, and that other components of the implant also can be removed or swapped out. This notion that something can't be uninstalled without surgery is an important notion, but I would also just point out that surgery itself is not necessarily such a huge barrier. Actually, almost everyone over the course of their life in the United States will have a surgery, if not more than one surgery. So really it's a question of making sure that it can be done in a safe manner rather than the concept of a surgery itself. DCKill97 asks, why can brain-computer interface technology only read from the brain and not write to it? The short answer is that brain-computer interface technology can both read from and write to the brain. Reading really means recording neural activity and decoding it, recording the electrical signals that the brain uses to communicate, and transforming those into command and control signals and ways of interaction with digital technology, computers, and the outside world. So that's really a translation problem. The other side of the coin is what people sometimes call writing into the brain, and that really means stimulating the brain in some way. In the context of current generation brain-computer interfaces, that stimulation takes place using electrical pulses, electrical stimulation. Those kinds of stimulation have been used to restore a sense of sensation, touch, vision, and also to stimulate the brain in other ways. Most of current generation brain-computer interface technology really is focused on the read and decode side of things. Reading and writing, or recording and stimulating, are actually quite different problems. You can't just sort of reverse the decoding into an encoder that writes information into the brain. It's not that simple. The field of genomics is one good example of this, in which the early 2000s saw an explosion in our ability to record or read and decode the human genome. And it wasn't until years later, really using almost a completely different form of technology, things like CRISPR for gene editing, that allowed gene modification in a scalable and programmatic way. Ulterior Kid 324 asks, how do you get a brain chip into the brain? Is the surgery long? The surgery is a relatively short surgery. General anesthesia will not always be required. It involves making a small incision in the scalp and an incision in the bone, but not necessarily removing a significant amount of bone. It will be an incision right about here. The electrode array itself, you can see it's very thin, and it gets slipped through an incision in the bone onto the surface of the brain. Right now, that whole process takes about an hour or two. In the future, it probably will be a little bit quicker. We foresee a future in which this can be done as a same-day surgery, much as a lot of surgery across the country is done. Piyush K. this side asks, think of a future where thoughts and feelings can be completely shared through a brain-computer interface surpassing the current limits of language. Will such a future be better or worse? I think we will eventually get to that future, and I think it will be a better future. I don't exactly know how we'll get there, and I'm sure there'll be trade-offs, but just like many forms of technology where you can't exactly predict what's going to happen, I think that's the case with brain-computer interfaces. Oli Driver asks, is anybody using AI to create a better brain-computer interface? Definitely yes. Actually, all brain-computer interfaces today use forms of artificial intelligence as a core part of how the interface works. It's important to understand that basically the problem of translating neural data into actions and interactions with digital technology, that is a translation problem, and that translation between neural code and digital code requires artificial intelligence and machine learning. But there's so many other applications of how artificial intelligence is involved in BCI. It's an extremely important and exciting area. Chrome Plated asks, how can I get involved in brain-computer interfaces and neurotechnology? There are a number of ways to get involved, but especially if you're a talented engineer, especially if you're a software engineer or have experience in modern machine learning techniques, I would invite you to apply to work with any of the companies that are working in the space today. Many of them are hiring. All right, that's it. That's all the questions. Hope you learned something. Until next time.